Hey, Physics 30s. So today we're going to be talking about Lenz's law, an interesting phenomenon in physics that pretty much is the basis of all our electricity in our house as well. So in a nutshell, Lenz's law is very similar to the generator effect. It's related to the generator effect, but it kind of this idea of the conservation of energy, where if I'm going to produce electrical energy by motion, there's got to be some kind of resistance. You can't get energy from just simply nothing. There's got to be resistance to that motion. And that's what Lenz's law says, that this induced current, so when I move a wire in a magnetic field, that's the generator effect, it's going to produce a current in that wire. Now, Lenz's law tells us which way the current is going to flow by saying that the flow of the current, the induced current, is going to oppose the direction of the applied force. So that means it's going to move in such a way that if I use my left-hand rule, it's going to push back on where it was coming from and slow down the motion. And we discussed that in the last video. We saw that, we talked about that with our hand rules, where the current started to flow one way, so we had to point our thumb in that direction, which also changed the direction of the force up or down, depending on which way we're moving the wire. We're going to talk about a couple of different shortcuts to do this and talk about how we determine the direction of the solenoid as well. And in one of my demonstrations, you can see that in action. All right, so a very simple application of this is just moving a magnet within a coil of wire. Now, to figure out which way the magnet is moving in the coil of wire, and I have a demonstration here. Let me just zoom in. So I have this magnet here. I can move it back and forth between here, and I can see that as I move it in, the current flows one way. As I move it out, the current flows the other way. So the faster I go, you can see the little voltmeter down at the bottom there. It goes one way when I move it in, it goes the other way when I move it out. And when I move it inwards, you can see that here, or you can see that down here, which way the current is flowing, right? So how we determine the direction the current is flowing is based on the idea that it's trying to stop the motion. So if I were to move this magnet inwards, so let's say that's the speed. For some reason, it doesn't want to save my writing. See, oh, just kind of disappearing on me. All right, so back to working here. So if I were to move this magnet in towards, I'll just use the purple here. So if I move this magnet, it's moving towards this coil of wire over here. And if it's moving in, the current that's going to produce, because as you move it in, you're going to change the magnetic field within the coils. And by changing magnetic fields, you produce a current. That's the generator effect. So a current is going to be produced here. And the current is going to produce its own magnetic field. That's what Oersted says. Moving charges produce magnetic field. It's going to produce a magnetic field in such a way that because this is a coil or a solenoid here, it's going to produce an electromagnet here that's going to try to oppose this north from coming towards it. So it's going to generate a north in this area here, and in turn, it'll also generate a south on the other side. So it's going to produce its own magnetic field here. It's got a north and a south. So that there is going to cause a force of repulsion, which is going to try to slow down this push. You're applying a force in here, so you applied a force to push it in. So there's going to be a magnetic force trying to push it back. And to get that magnetic force to push back, there has to be a north produced on the solenoid closest to the north side of the magnet because it's moving towards. So now what you're going to do is you're going to pull out your left hand and you're going to put your thumb in that direction. Because this is the solenoid rule, so I can put this is going to be the one where you curl. My thumb is the north of my solenoid. So I can put my thumb in the direction of the north. And my fingers are going to show me which way the current is going to flow through this. And because I'm using my left hand, this is electron flow. I can use my right hand and determine conventional flow, because that's what's going to show on the application here. So it's going to wrap around. It's going to go over the top and down the front, because my thumb is pointed towards the north there. So if I were to draw in the current, it's going to go over the top and then down the front, over the top and then down the front. So if I follow the path of the wires, you can see that's going to go over the top, down the front, through the device here, and then back up the back side and continue wrapping around. So that's an electron flow when we do that one. Now, what's going to happen on the application is it's going to probably be conventional flow. So if I move this in, rather than coming out down here, like downwards, it's probably going to show an arrow going upwards instead. Let's just see. Yeah. So they're showing conventional current. This is the National Meg Lab. They're from the United States, so they still teach conventional current, but they do know electrons flow down in the States. Now, when I move it out, you can see that the current goes the opposite direction. So let's think about what happens there when I start moving that out. So let me just erase what's here. Okay, so when I move it out now, so the direction of this is going to go this way. So that's my applied force. That's the direction the magnet is moving. When I do that, the current that's being induced is going to try to stop that magnet from moving again. It's the change in magnetic field as I move it outwards, so the magnetic field is decreasing. But even though it's decreasing or increasing, it's still going to produce a magnetic field. It's going to induce a current here. That's going to produce a magnetic field. But it wants to stop that motion. It wants to stop it. So it's going to produce a south here this time rather than a north. And there's going to be a north on this side. So if I use my hand rule now, I'm going to put my thumb in the direction of the north. My fingers are curling the other direction now. So they're going to go over the front and then down the back. So my electron flow is going to go this way. So they're going to come down the back. They're going to up the front, sorry, and then down the back. So they're going to come down this wire here. And that's the direction. That's why it's going the other direction. Okay. So that's what's happening in Lenz's law. It's trying to stop the motion of whatever is causing the induced current. In this case, by moving the magnet. And sometimes they just be moving the wire within a magnetic field. And we saw that in the generator effect as well. All right. So at this point, what I want you to do is I want you to stop this video, right? Pause it, and then go watch the eddy current video, and possibly at the same time you can watch the physics asylum video. This time I'm going to introduce you to my favorite YouTube physicist, Nick Lucid. Some of the stuff he talks about in his videos are beyond this course, but he's engaging, he's captivating, sorry, and he has some great visuals. Some classes like him, some classes don't. I really do. You're going to see a bunch of his videos in the future here. You can watch both his videos. What is magnetism? But the most important one is turning magnetism into electricity. All right, so pause the video, and I'll see you in a bit. Okay, so I hope you enjoyed those videos. So in the eddy current, I'll talk about the eddy current one in a second here. I just want to talk more about this. This is very similar to how the eddy current system works. So you have to imagine that the copper tube in that demonstration is just a coil, a really, really tightly bound coil of copper. Copper is not magnetic, but it does allow current to flow through it. So I can produce an electromagnet from it as long as I get current flowing through it. So in this little diagram that we have here, so say we have this north that's moving towards this coil of wire. If there's a north moving towards this coil of wire, there's going to be a north that's generated over here. You can see I already had it there before to try to oppose this motion. So it wants to push back on that magnet. So I apply a force on this. To stop it, there's got to be some kind of resistance, in this case, a magnetic force to slow it down. And obviously you can easily overcome it. In that demonstration with the eddy current, gravity easily overcame that resistance force, but it slowed it down enough that you can actually see it slow down. If I were to cut this and current wasn't able to flow through this, then that magnet would just freely flow through. It'd be really easy to push it. So using our hand rule, you can see here, if I put my hand in there, my thumb in the right direction here. Oh yeah, sorry. Put my thumb in the right direction. So it's going to go this way. You can see my fingers are going up the front and then down the back. And you can see that's what's happening here in the current. It's going up the front. Okay, that's a bad marker to use. It's going up the front and then down the back. So up the front, then down the back. Okay? So what interaction would the magnet have? It would be repelled. All right? It would be slowed down, right? Just enough that you would notice the resistance there. All right, so here's another question here. So if I were to move this magnet in towards the coil wire here, you can kind of see the dotted area here is behind and the solid area is in the front. So this is going to move inside here. So if I move the magnet in towards this coil, it's going to induce a current because of a change in magnetic field, and it's going to induce a current in such a way to try to oppose this. So there's going to be a south side produced here to cause a repulsion force to try to push this magnet back. So there's going to be a north on this side. So I'm going to use my hand rule. I'm going to put my thumb in the direction of the north. It's going to wrap around, so up the front and then down the back. So it's going to go up the front and then down the back. So it's going to go down the back. So up the front and then down the back. So if I follow my little current, it's going to travel to the right. Or sorry, this is to the left. Through G, or through G. And G could be anything. It could be a light bulb. It could be an ammeter, a galvanometer again. Just could be anything that would allow current to flow through it. All right, so if I do another one here, so here's another magnet. Now this magnet is now moving away. You can see that the north is moving away. So it's going to try to stop that. So the current is going to be produced in here. It's going to be induced in here. It's going to try to stop that. So there's going to be a south side on this side and a north side. That's the same orientation as the last one. So it's going to go up the front, down the back, up the front, down the back, and through to the left again. All right. So these are pretty easy. You're just using your hand rule, the second hand rule, after you determine where the north and the south of the electromagnet is, so the solenoid, then you can determine which way the current is flowing based on your finger motion. Okay, here's another one here. Oh, this time we're actually moving the coil wire around a magnet. Now, that's just the same thing. It's all relative. So if I move the coil, the magnetic field is changing because you're moving the coil towards a magnet. So I'm going to induce a current, but it's going to induce a current to try to stop the motion. Again, so it's going to put a south here on this end to repel, or to stop itself pretty much, or to repel the south away. So I can use my hand rule again. So it's all the same here. It's going up the front and then down the back. So again, it's going left through that G point there. Okay. Here's another version of Lenz's law. This is more the generator effect. If I were to move a straight wire through a magnetic field, what happens? So this one, we're going to use our left-hand rule, the third one, with the palm on it, to figure this out. So we're going to move. So remember that what's inside these is a bunch of electrons. So we're going to move these electrons here to the right. So we're moving to the right. So what I'm going to do is I'm going to put my thumb to the right. The little X's here, they represent the magnetic field. So I'm going to put my fingers into the page. My fingers into the page. My thumb to the right. And then I notice that my palm is facing downwards. Okay? So down to the bottom of the page. So all these electrons, all these little electrons in here, they're going to get forced downwards. Sorry, I'm erasing them by accident. Okay. So all of these electrons start moving down. So they all go downwards. I'm just going to use a thicker pen here. So they're all going down now. So they all start moving this way. So that's the electron flow. So I'm reduced in current. So the current has started moving downwards. But because the current has started moving downwards, that's the direction the electrons are moving. So I'm going to put my thumb downwards now. All right? My fingers are still going into the page. So then you notice that my palm is facing over to the left. So that means all the electrons here are now going to be forced to the left. They're all going to go back here. All these electrons are going to go back. And you notice that that direction, the electron, the force that the electrons get pushed back on the wire are is opposite the direction that we moved the wire. So we took the wire, we moved it to the left. So here's my wire. We moved it to the right. So we took this whole wire, we moved it to the right. The electrons flowed down through it. And then because of that, the electrons started pushing back on the wire to try to give me a little bit of resistance. So I'm not able to just freely move that thing to the right. It's going to be a little bit of resistance to it. So, direction of flow moves perpendicularly. Yeah, so we do know that based on what's happening here, the electron's going to flow downwards. So they're going to go down and continue the loop here. But because of that, there's going to be a little bit of resistance. There's going to be a little bit of pushback to it. So these are the same here. So if I were to move the, oh, this is just the same picture, isn't it? Let me just double check. Yeah, that's just B here. That's just B all over again. Now, so let's say I did this one. So I'm moving the electrons in the wire to the left. Okay, so use my hand rule. I'm moving it to the left. The magnetic field, sorry, my magnetic field is actually coming out of the page. So my fingers are going to come out of the page. My thumb is to the left. My palm is down. So these electrons are going to go down and through this way. So that's the way the electrons will go. But because the electrons are moving down, so I'm going to point my fingers down, and then you notice that my palm is pointing to the right. So there's going to be a resistance here. So these electrons are going to give me a little resistance. They're going to all kind of push back a little bit. But it's most likely that's not going to be able to overcome the force that you're pulling the wire over to the, in this case, to the right or to the left, sorry. So I should be able to easily do that. I should be able to easily move this sideways. It should, but there will be a resistance there. All right, so I have no idea why I have this last little picture here. What I want you to do is maybe you just want to try this question out, try to determine how fast these electrons are moving. You can see there's a few things about this. They're going through undeflected. This picture will show up again in the second last chapter when we talk about the atomic theories. Okay. So what I want you to do now is, if you could stop this video, work on some of the activities. I'm going to give you guys a review sheet. Work on the assignments, this week's assignment as well, and maybe watch the last video there. I believe I have another demonstration about Lenz's law and how there's resistance to producing electricity. I'll see you in the next unit. Bye.